let's talk about graph search. That's one of my children. All right, so here these right. So the problem is you're given a graph and you're given a start node, and you want to find all the nodes that are reachable, right? So one operation is you say, well, my invariant might be that I already know that U is reachable, and then I'll say that I found U because I've when I find it, I know there's a path to it, and then well, when I find U, I have to kind of handle it, and by handling it, I follow its edges, and I then find V, and then I say, well, V is reachable, right, by transitivity, right? If from S I can get from U, and there's an edge from U to V, then I can get to V, right? So that's what we do, right? And so you can start by sort of branching out and finding what you can find. But of course, if there's cycles, right, you don't want to be doing it again. How do we avoid going around and around? Yeah, it's just like, I don't know if you know Hansel and Gretel, they drop breadcrumbs, right? So when you go around, when you get to a node, you drop a breadcrumb so you know you've been there before, right? So so here, what you can do is you can start at S and go out here, and then we can say, oh, we found A, so you can go out from A, and you can keep going out from things, right? And then you can say, well, now we're defining our invariants, right? Our invariants might be that if we've found a node, all nodes are either found or not, and if they're found, we've either handled it or not. So if it's found, it means that we know that there's a path from S to it. Why? Because we've traced it out, right? And if it's handled, then that means we've already looked at its edges, right? We've searched out, and that gives us the extra loop invariant that if it's handled, then all its neighbors have been found, right? Does that make sense? So the algorithm is you start with S is found but not handled, right? So then we're going to handle it. What does that mean? You find its neighbors, and then you choose one of its neighbors, now A has been found and not handled, right? So we handle A, and then you choose some other number. Here, D is found but not handled, so we handle it, right? And that's going to be the algorithm, and this maintains the loop invariant, because when you handle a node, then you find its neighbors, which you know are reachable, and when you handle a node, you make sure its neighbors are found, right? So we're maintaining these loop invariants, right? So, and then how do we make progress? Well, you could say the measure of progress is the number of nodes that have been found so far, right? But you may do a lot of work and not find any new nodes. You might find nodes that you've seen before, or a node might not have any neighbors, right? So we want to make our measure of progress is that you make progress every iteration, and so this isn't a good measure. But if our measure is how many nodes have been handled, right? Every iteration we handle a new node, right? And you only have n nodes, so you can do this at most n times, right? And so how do we start? As I've said, S is found, right? We're searching out from S, so we found S. We know there's a path from S to S, and but it's not handled. and all the other nodes haven't been found, right? And when do you stop? Well, yeah. We're not doing the number of found nodes because we might not make progress. Handle nodes, okay. Yeah.
They have like common neighbor, and how would that work?
It's just that all we're wanting is that for the measure of progress is that it goes up every iteration. And these two nodes weren't handled, and I handled this one, and I handled this one. Now they're both handled, right? Right. And so when can we stop? Well, you could stop when you've found all the nodes, right? But some nodes might not be reachable. That's the whole point. Yeah? I don't know what an empty node is. A node with no out edges? Yeah, for sure. For sure. In fact, there it is, right there. There's a node that has no edges in or out. Right? This one down here. Right? So we might not find them all, right? So you want to say, well, when are we going to stop this algorithm? One time to stop is when you don't know what to do anymore, right? When you get stuck. And so what is our algorithm? Is to take a node that you have found, but you haven't handled, and handle it. And when do you get stuck? When all the nodes that have been found have already been handled, right? That's when you get stuck. So we're going to stop when all found nodes have been handled, right? So if you want code, it's pretty straightforward. We start with no hand, right? The numbers that have, the set of nodes that have been handled is empty, and the set of nodes that are found and not handled is just S. And then what do? We exit when there are no nodes that are found and not handled. And what do we do otherwise? Is you take some node that is found and not handled and handle it, right? How do you do that? You look at all the edges, all nodes that it's adjacent to, all V's, and you say, well, if V hasn't previously been found, then say it's found and not handled. If it's already been found, then you ignore it, right? And that's the algorithm. Everybody kind of follow that? And so we exit when all the nodes that are found are handled, right? So these are the three things, the loop invariants we have, and this is the exit condition we have. And what's our post condition? That all nodes that are reachable have been found, right? So that's what we want. We want to output the found nodes, and here the set found equals the set handled. That's what we're going to output, right? And we need to do this. We have to prove that this works. We have to prove two things. We have to prove that if a node is found, then it's reachable, right? And we also have to prove that if it's reachable, then we will find it, right? Everybody see those two statements? And remember, I'm going to now ask a trick question that nobody ever gets. It's, remember, the way we prove the post condition is we know that the loop invariant's true, so we know this and this, and we know the exit condition is true. Why do we know the loop invariant's true? It's because we've maintained it. Why do we know the exit condition's true? Because we exited, right? And so just using logic, which we're all experts at, right? We want to say from these three statements, we want to prove these statements, right? So the first question is, if you know this and you know this and you know this, how do you prove that found nodes are reachable? Yeah, I'm going to go, you're adding meaning to that, right? We found them, that means we trusted a path. Well, I'm just using the loop invariance, right? And the loop invariant right here, right there, says if you found it, then there's a path to it, right? So this first statement is trivially follows from the loop invariant, right? So that's, this one here is just there, right? And so now we have to do the other. We have to say, if it's reachable, then we find it, right? And everybody remember that A implies B means not B implies not A, right? Contrapositive. So we can turn this around and say, if you haven't found it, then it's not reachable, right? Everybody see that's the same? So the proof I call the Great Wall of China proof. We build a big wall around the nodes that have been found, right? This, remember, the set found equals the set handled, right? So this is the set of nodes that are found, it's the set of nodes that are handled, and we put a big wall around it. And the guys outside have not been found, right? And we want to prove that the guys outside of the wall are not reachable, right? There's no path from S to them, right? And why is that? It's because there's no way to cross the wall. It's a big wall, right? People see why there's no wall here? Well, what do we know about a node on this side of the wall? Well, nodes on this wall side are handled, right? What's the definition of a node on this side? It's not found, right? So can you have an edge crossing the wall? No, because our invariant says that if you've handled it, then you've found the neighbors, right? And we've handled this because it's in this set. We haven't found this, so you have no edges leaving, right? That makes sense? And that tells us there's no edges. And that tells me if you're outside of the city walls, there's no getting to you, right? Does that make sense? All right, so there we've just proven that this algorithm solves our problem, right? Everybody buy that? Which it's not too surprising. It's a simple algorithm, works. All right, what's the running time is, well, we have to handle all the nodes, right? And how many nodes are there? They're in nodes. And each node, you have to handle all the edges, all the neighbors, right? And how many neighbors might you have? Well, you might have n neighbors. And so then you could argue this algorithm could take n squared time, right? But we can do a little better than that, is because if you consider any edge of the graph, we visit it only at most twice. Why is that? Well, if it's a directed edge, you visit it once. You're here and you go to your neighbor. That's once. But if it's undirected, you're here, you go there, and then now you're there and you go here, right? So you kind of examine each edge twice. And so the total running time is proportional to the number of edges, right? Another way of thinking about it is each node that you handle, here if I'm handling this node, then I have to handle its edges, right? And so the time to handle a node is proportional to its degree, right? And so then the time is the sum of the degrees, and the sum of the degrees is the same as the number of edges, right? Everybody kind of good with that? So the running time of this is proportional to the number of edges, and I would say that's as good as you can do, because I would actually call that linear time. Why is it linear time? Well, because the amount of space to represent the graph is you have to write down all the edges, right? So the size of the graph is really the number of edges to write it down, to communicate it. And this is linear in that size.